with 5 group presenters within. And allow me now to invite our session chair. Please welcome Professor Nathaniel Oko from the Philippines. Let's give a warm of applause. So, Professor Nathaniel Oko, I will hand over the session to you.
Thank you very much, Madam. So pleasant afternoon to everyone. This is, again, oral session number 6. We have 5 papers. My name is Nathaniel Oko. I'm a senior lecturer from De La Salle University, the Philippines. So we have 5 papers. Let me go through some housekeeping items before we start. So each presentation is given 16 minutes, 13 minutes for presentation proper, 3 minutes for question and answer. We have a bell at the back, so 1 bell means 3 minutes left. A series of bells ringing means time is up. We also have several colleagues who are joining us online. So those who have questions and those who are joining online, please feel free to utilize the chat function. So let's now go through the first paper titled Measuring Emotion Preservation in Expressive Speech-to-Speech Translation. The authors are Bagus Tris, Toru Shirai, and Sakriyani Sakti. So please, the time is now yours.
Nathaniel Oko. So I am Bagus from NICE. So in this presentation, I would like to present our work entitled Measuring Emotion Preservation in Expressive Speech-to-Speech Translation. So we conducted this research with Toru Shirai and Professor Sakriyani Sakti. Move to the introduction. Okay, before that, this is the overview of our presentation. The first, I will be introducing the background and research scope from the previous research, and then what dataset and methods we used. And then our main proposal is evaluation metrics. And then we saw the result, and finally we will conclude in the end of this presentation. So in speech-to-speech translation, in expressive speech-to-speech translation, there are at least 2 different things that should be measured. The first is linguistic content, and we already have some metrics like Brew, Comet, and others, which is very rigid. And the second one is emotional expression across languages. So for example, if you want to translate expressive speech from English to Indonesia, or from English to Japan, or from English to German, we want to keep both content. The first is linguistic content, and then second one is expressive content. And from the second one, there is, I think, until now, there is no main metrics, no rigid metrics to measure the nuance, the expressiveness in speech from the source to target language. And the current evaluation based on the embedding similarities between source and target, and the second one is based on the prosody. And we know that some prosody may be not related to emotion. So this is not an indirect measurement. And we propose to direct assessment using the speech emotion recognition model. It means if in the source language, the utterance is happy, in the target language, if it is translated to Japanese or other language, it should be also happy too, not angry or a different emotion. So we want to know how to measure or how to judge this measurement. And contribution of our research, we proposed 3 different metrics. The first is balance accuracy ratio, the ratio of accuracy between the source and target, and the second one is emotion preservation rate, and the last one is the coherence kappas between the source and target language. And we also demonstrate that embedding-based similarity, which is used until now, may not really indicate emotion preservation. It means if we measure the embedding in source and then we compare it in the target language and we measure the similarity, that similarity may be not reflected the expressiveness of input languages. And we also use the other metrics like the valence arousal sim. Okay. And pause rate, speech rate, and others. In short conclusion, we saw that half of emotion is transferred from the source to target language in our data and in the used dataset, which is MLD datasets. So what is MELT ST dataset? If you're working in expressiveness or emotion recognition, there are already MELD dataset, MELT dataset. It's derived from the Friends drama. If you watching, I think some 20 years ago, 10 years ago, this drama is very famous in RCTI, I think, Indonesia. And they use this kind of drama to demonstrate the expressiveness in speech. And this dataset already transferred or translated into 2 languages. One is to Japanese and another is to German by researcher in Kyoto University. And this dataset contains 7 emotion categories like anger, disgust, fear, joy, neutral, sadness, and surprise. So we propose to measure the expressiveness in source to target language using SER, speech emotion recognition model, using the same model for the source and target. The feature on the acoustic embedding we evaluated is emotion to fact plus large, which is claimed as the most expressive acoustic embedding until now. It contains 1,024 dimensions, and also the author claimed that it is language independent. It can be used in any language like Indonesian, Japanese, English, and others. Although maybe the training data come from English dataset. And for the model, for the emotion model, we use MLP, multi-layer perceptron, with 2 models, except the output. The first model, in the first layer is 64 nodes, and the second layer is 32 nodes. The output layer is 7 nodes, represented 7 emotion. And also we use dropout about 30%. And for training, we use a small training patch to training patch, and the maximum epoch is 80. And we also address class imbalance using cluster centroids, and all implementation are applied in Kululeko Toolkit in Python. So here is 3 our proposed metrics. The first is BAR, balance accuracy ratio, which count ratio between the target. UA is unweighted accuracy between target, and UA of the source or source target. So it means if the expressiveness is transferred from the source to target, the value of BAR is close to 1 here. However, maybe even the BAR is close to 1, for example, 0.8 or 0.9, there are differences in samples because the accuracy, only the total accuracy. So we also propose the second one, we call it as emotion preservation rate, or EPR. So it counts the number of the same level between a target and source. As I said previously, if the target is happy, if the source is happy, the target should be also happy, and we count the same occurrence and count the total. So also, if emotion is preserved in source to target, the EPR value should be close to 1 also. And the next one also we apply Cohen-Kappa. It's agreement. If you use statistics, it's agreement between 2 annotator or 2 reviewer, and we treat the source and target as a different annotator or different writer. So also if it will also, I think, close to 1 for the high agreement between 2 annotators. And besides those 3 metrics, we also evaluated other metrics that already used in our community. The first is EmoSim. So it is the frame level cosine similarity of emotion to fact embedding, which we use as the acoustic feature. And the next one is VA-SIM, valence arousal similarity. So we predict the valence of the source and the valence of the target, and we count, or we count the similarity between this valence and arousal. And the next 4, I think, is proposed by Mita. The first one is auto-PCP, utterance level prosodic similarity using XLS R53 embeddings. The second one is the vocal style similarity using WebLM large embedding. The next one is pause rate, which is Spearman correlation of pause rate between source and target. And the last one is speaker rate, also the Spearman correlation of speech rate between source and target. And here's our result. So we evaluated in this only one data set because we only found this data set that has been translated into from English to Japanese and German. However, there are two translations. First is the Japanese and Japan, and we can see there that there is differences between value like PAR. We obtain about 57%, and then EPR very low value, 20%, kappa also very low. It shows that or maybe very little emotion or expressiveness transfer from the source to the language. And the result between the two languages, I think, similar. The English to Japan and English to Dutch also show similar pattern. Can I take to my slide? Okay, I can tell that the between Japanese and Germany or Dutch, the pattern is similar, but the value is different. And we can see that some value of this matrix are similar, like the PAR and then VASIM, and also I think pause rate also about 50%. And we obtain high value. In previous result, we can see that let's say high value in emotion similarity. However, that because we use the same embeddings between the source and target, if the real correlation is high, the score of accuracy should be similar. I mean, if the scores of accuracy performance in source is about 70% or 50%, also the score of performance in the target language should be similar because there is high similarity. But we found the opposite, that the score of the performance between source and target is very different. So it means that this emotion similarity didn't reflect the real transfer of expressiveness between two languages. And for valence arousal similarity, we see the similar pattern between valence arousal for Japan and also for German, about 54% for Japan and 55% for German. And it's I think it's more consistent with discrete emotion. And it may be more reliable indicator for emotion pressure rather than the emotion similarity. And yeah, there are at least three similar values there. The first is PER, balance equity ratio, and then the second one is VASIM, the previous one, the valence arousal similarity, and the last one is the pause rate correlation. All of these three values is about 50%, so about 50% of the transferred emotion between source and target. And we found the diverse pattern in VASIM and speech rate, so that two metrics may be not suitable. And across all experiments, we saw that the measurement of expressiveness in speech translation is process dependent. We can show from the first result that it is not language independent, but it's process dependent. So it's about how we translate the expressiveness from one language rather than the language specific. So, and also we compare the performance of the emotion model. As I said previously, if the emotion similarity show high correlation, it's also shown the similar score for performance. However, we found that for Japanese, for example, we obtain about 48% of accuracy, but for in the source for English, but in the target we only obtain about half. And also we found that this difference is consistent across two languages, for Japan and for Dutch or German. And we can see here that this is the original confusion matrix in the top, and the same English but speaks differently because the sample is different if you remember my previous slides. And in the bottom we can see that the diagonal pattern is not appear like in the top figures. And lastly, also we analyze the uncertainty between the two languages. In the left is the model uncertainty between English and Japan, and in the right is the uncertainty and model uncertainty between English and German. So if the expressiveness in language is transferred, it should be in the left bottom. But we can see in the both translation in Japanese and in German that the most dots appear in the top right. It means that it's not transferred. The emotion is not transferred here in the translation. So maybe it support the previous finding that only about 50% emotion or expressiveness is transferred from the source to target language. So we can conclude that we already proposed some evaluation to measure how expressiveness in speech-to-speech translation is preserved from one language from the source to target. And we found about the half of emotion is preserved, and we found at least 3 valuable metrics, PER, VASIM, and pause rate. And also we found that emotion similarity is not very related to emotion preservation. I think that's all from my side. Thank you very much.
Thank you very much. Let's give the presenter a warm round of applause. So I believe we still have time for questions. Do you have questions from the audience? So I'll probably ask the first question. I probably missed it in the slides, but are paralinguistic vocalization included in the study? For example, laughter, crying, gasp, are they included?
No, there is no non-verbal. I think only the verbal communication in this data set.
Okay. And then, no questions. On slide 10, it was mentioned that you have a kappa of around 0.02, which is a bit low.
Yes.
My understanding is acceptable kappa rates are in the range of at least 0.6.
Yes.
Do you have explanation on why that is the case?
So that's why we saw that here that the kappa is very low. It means that the expressiveness or the emotion is not transferred from the source to language. So if the emotion is transferred from the source, for example, in English there is a lot of emotion like happy, and then in the target should be happy also. So this kappa score should be high, and we found that it's very low. It means that the expressiveness in the source is not transferred to the target language.
Okay. Do we have questions from the audience? One final question on my end. What are the next steps? Is this part of a bigger project? Are there plans to commercialize, deploy?
Yeah, so the next target is that we have that the new data set is so low expressiveness, so we want to improve the MELT ST, maybe, for example, and we can use our metrics to measure if there is any improvement from the baseline, this baseline. So this could be as baseline to improve the expressiveness in speech translation.
And hopefully achieve a kappa score of at least 0.6.
Yeah, I think, yeah.
Okay, let's thank the speaker with a warm round of applause.
Thank you very much.
Thank you very much. So we will now proceed with the second paper, Generation and Automatic Evaluation of SOAP Notes from Medical Dialogue Using Large Language Models. The authors are Tsubasa Saito, Rikuto Yamanaka, Yuko Wakabayashi, and Norihide Kitaoka. Yeah, could we request for his slides to be presented?
Hello everyone, I'm going to about our research. The title is Generation and Automatic Evaluation of SOAP Notes from Medical Dialogue using Large Language Models. We are researching how to generate electronic medical records from conversations using LLM and medical data. First, I will explain the background. Making a medical record is hard work for nurses. In Japan, nurses spend about 20% of their time writing reports. This means less time for patients. It also causes burnout. They use the SOAP note format. Subjective is what the patient says. Objective is data like vital signs. These are facts, but assessment and plan are more difficult. The nurses must think hard to make a judgment and a plan. So our purpose is to make SOAP notes automatically using ASR model and LLM. The top picture is traditional EHR operations. A nurse talks to a patient. Then the nurse must write the SOAP note from memory. This is slow. The bottom picture is our system. The conversation audio is recorded. ASR model write down the text. Then an LLM helps write the SOAP draft. My research focuses on this part. Using LLM to generate SOAP notes from the ASR text. This is a support tool. We assume the nurse must still check and edit the draft before saving it. We look at past research. First, a study by Asghari. Their research was about generating SOAP notes from dialogue and evaluating their safety. But their work had problems. It tested only one LL model. It didn't test advanced methods like RAG. And evaluation was done by human experts, which is slow and expensive. Second research in Japan, like Ishikawa's. And their research was about generating summary reports from old medical records. The problem is that most research in Japan uses static text or reports. Very few studies use real-time conversation like we do. So there is limited research on two key areas. First, SOAP notes generation in Japan, and second, automated evaluation of medical documentation. We have two main contributions. First, our goal is to improve the accuracy of SOAP notes generation. We propose a new prompt strategy to do this. This strategy combines two things, RAG and a reason and evidence prompt. This prompt forces the LLM to be accurate and stop hallucinations. Our second contribution is to solve the evaluation problem. As we saw, human evaluation is very slow and expensive, so we validate the LLM as a judge framework. We test if one LLM can reliability check another LLM for safety, specifically for Japanese medical text. We tested three different methods. First is base method. This is a simple method. The LLM gets the dialogue text, nursing plans, and previous SOAP to make the new SOAP notes. A nursing plan is what kind of care the patient needs and how to help reach their health goals. Second is base plus RAG method. We also give the LLM related documents from our database of old records. We hoped this would help the LLM learn the hospital's style. Third is our new idea, best plus reason method. We tell the LLM to write why it made the content and where the information came from in the dialogue. We hoped this would stop hallucinations. By having LLM generate fact-based responses, we aim to suppress hallucinations. For our experiment, we test two LLMs, GPT-4o, which is fast, and O-Mini, which is good at thinking. Our data was 10 days of real dialogues from two patients. We manually transcribed those dialogue recordings. The RAG database had 200,000 old stop notes. For evaluation, safety was most important. We counted hallucinations and omissions. Here are our results. This table shows the human evaluation. 7 expert nurses checked all the stop notes. For the numbers, lower is better. The most important findings is GPT-4o with our best plus reason method got the lowest hallucinations, only 0.14. This is very good for safety. But we found a problem. Methods that were good at stopping hallucinations were not always good at stopping omissions. Best plus reason had 1.0 omission, same as the baseline. Let's look closer at the methods. Our best plus reason method was very good at stopping hallucinations. It went from 0.43 down to 0.14. This shows our idea was correct. But best plus RAG method made things worse. It increases hallucinations. Why did RAG fail? Because the similar cases from the database were often not a good match. They were about different patient problems. This confused the LLM. Next, we compared the two models. For accuracy, there was no big difference. The results were very close. The biggest difference was speed. GPT-4 was 2 to 3 times faster, so we think GPT-4o is more useful for this task. Our second big idea was testing the LLM judge. We used another LLM O3 mini to check the soap notes just like the human experts. This table compares the LLM judge score with the human expert scores. We found two key things. First, agreement. The LLM judge and the human nurses agreed on the best method. Both chose GPT-4o with best plus reason as the best. Second difference, the LLM judge was much stricter than humans. It found many more errors. For example, humans found 0.14 hallucinations, but LLM found 0.6. Why? This is because the LLM judge made many false detections. This means it found errors that were not accurately errors. This lowered the agreement with the human experts. Our conclusion is that LLM judge is useful for finding the best method, but it is not perfect represent for humans yet. So what does this all mean? First, our best persuasion method works well to stop hallucinations, but it was a trade-off. It misses more information we need to fix this. Second, why did lag fail? Because of noise. The research results were often unrelated and confused the LLM. And context contamination. The LLM copied old records and missed new patient information. Finally, the LLM judge. The good news is the LLM judge and human agreed on the best method. The bad news is their detailed checks were not the same. So it cannot replace human experts yet. To conclude, we have 4 main findings. First, telling the LLM to show reason and evidence is a very good way to stop hallucinations. Second, lag didn't help in our test. Third, GPT-4 was the most useful model because it is fast. And fourth, the LLM as a judge is a good idea, but it cannot replace human experts yet. For future work, we will use more patient data, improve lag, improve the LLM as a judge, and test the system with real speech recognition errors. Thank you for attention.
Thank you very much. Let's thank the speaker. Do we have questions from the audience? Maybe I'll start. I probably did not see it in the slide, but is the language domain English or Japanese? Is this for Japanese or is this for English? The language.
Its data is Japanese.
Japanese. Okay. Thank
Sorry.
you very much. Do we have questions from the audience? So I'll ask again, do you have an example of a hallucination?
Hallucination example. For example, temperature was felt horse dead. For example, patient and nurses conversation in 36 Celsius. But the LLM hallucinated to 35 Celsius.
Yeah. If that's the
Yes.
case, what is an example of a noise?
Example noise.
Yes.
Yeah. So such as another patient's temperature data confuse elements.
Okay.
Sorry.
Okay. And then for each soap, what is the usual number of words? For soap notes, what is the number of words? What is the average number of words in each soap notes? The number of words in a soap note.
Word in soap was generated in Japanese, so 500 character.
500 characters.
Yeah.
That's the average for one soap note.
Yeah.
Okay. Okay, do we have other questions from the audience? If none, then let's thank the speaker once more with a warm round of applause. Thank you very much.
Thank you.
So we will move on to the third paper in this session, Tuning Tone with Age, Adapting Dialogue Response Generation Based on LLMs and Self-Supervised Speaker Age Estimation. The authors are Riki Yagi, Wang Zhu Qi Gyo, Hong Wei Wu, Yuta Hirano, and Sakriyani Sakti. So the floor is now yours.
Yes, so hello everyone. My name is Rich Yaji from Japan, Todaiji Gakuen High School, working with NICE. Today I'm going to present our research titled Tuning Tone with Age, Adapting Dialogue Response Generation based on LLMs and self-supervised speaker age estimation. Here is today's outline. So I'll talk about background first. First, in the early stage, dialogue systems mainly worked as simple question and answer tools. So, Yes. Sorry. So they were designed for specific tasks and focusing on accuracy and task completion rather than real conversation. So the interaction was rigid and one-way without any empathy or personalization. So this led to very limited and mechanical communication. With deep learning, dialogue systems evolved into conversational partners that can talk naturally with users. Recent systems focus on politeness and user comfort, trying to make interactions smoother. However, they still ignore users' attributes, such as age or gender, and which can cause unnatural or distant communication, even in polite conversations. So therefore, our goal is to create an age-aware spoken dialogue system. It can recognize the speaker's age and adapt both the tone of language and the speaking voice. By integrating several technologies, self-supervised learning, SSL for age estimation, and large language models, LLM for dialogue generation, and text-to-speech, TTS for output. So we aim to make human-AI interaction more natural and empathic. So here is an example of how our system adapts its tone depending on the speaker's age. So on the left, you can see a formal and natural neutral response, while on the right, the system uses a friendlier, more casual tone, so which is more suitable for a younger speaker. Yes. So I'll talk about related work. In a dialogue system, studies like GenPads focused on politeness using reinforcement learning. These systems adapt to mood or feedback, but they don't handle fixed traits like age. For age estimation, early methods used simple acoustic features, which were not very accurate. Then came LSTM models, and recently self-supervised learning, or SSL, has shown much higher accuracy. So Our work combines these ideas, and we integrate SSL-based age estimation into a dialogue system to make age-aware conversations possible. So here is our system. Our system has three main parts. First, user information extraction. And second, contextual response generation. And third, dynamic voice synthesis. So, and the input is a user's speech, and the output is a synthetic voice reply adjusted to the user's age. First, when a user speaks, the audio is sent to in two models in parallel. One is an automatic speech recognition, ASR model, which converts speech to text. And the other is an age estimation model that predicts the speaker's age from voice features such as pitch, timbre, and rhythm. In this way, we got both the content of the message and who is speaking. Next, both the recognized text and the estimated age are sent to an LLM. The LLM receives a special prompt telling it to choose the response style. So if the user is under 30, respond in a friendly tone. And if 30 or over, use polite language. For example, for Japanese, we will use keigo. The LLM then generates the most suitable response text. Finally, the generated text goes to the TTS model for speech synthesis. Depending on the estimated age, for users under 30, the system speaks in teenager's voice, which sounds younger and casual. And for users 30 or older, it uses an adult voice and giving a more mature impression. This process allows age-appropriate speech output and makes the dialogue more natural. So here is the experiment settings. For dataset, which used to train age estimation model also, we used AgeBox Celeb, which is an English dataset and containing about 168,000 samples from 5,000 speakers. And for ASR, we used Whisper. And for LLM, we used Grok 3. And finally, for TTS, we used your TTS. And we evaluated the system in two ways. For age estimation, we used mean absolute error, MAE, per age group. And for speech naturalness, we used NISQA, which predicts mean option score most on a 1 to 5 scale. And a higher most means better speech quality. And we compared two models, a baseline F-bank model, which uses simple acoustic features, and an SSL model based on WebLM, a pre-trained large model. Both were trained with a 4-layer transformer encoder for age classification from 5 to 95 years. So I'll talk about results. As shown in the figure, the SSL-based WebLM model clearly outperformed the F-bank model across all age groups. The best accuracy was in the 30s age group, which has the most training data. For older groups like 70s or 80s, accuracy was still lower because of data imbalance. Overall, self-supervised learning proved very effective for age estimation. Next, we compared the quality of synthetic voices with the original training audio. The NISQA predicted most values of synthesized speech were higher in almost all cases. For example, the Japanese teenager's voice improved from 2.02 to 3.13, and the English version from 3.10 to 3.27. This shows that our TTS model produced clearer and more natural voices than the original data. And here is the usage example. So I will show the video.
Good afternoon. It's a lovely day today, isn't it? I hope everything is going well on your side. It's always nice to have a little conversation like this.
Yes, it's definitely a lovely day today. Everything's going great here. Thanks for asking. It's always nice to chat with you too. What have you been up to today?
Good afternoon. It's a lovely day today, isn't it? I hope everything is going well on your side. It's always nice to have a little conversation like this.
Good afternoon. Indeed, it is a lovely day today. Thank you for your kind words. Everything is going well on my side. I appreciate the opportunity to have a pleasant conversation with you. I hope your day continues to be enjoyable.
Yes, so that's it. In conclusion, we built an age-aware spoken dialogue system combining SSL age estimation and ASAR and LLM and TTS. The SSL model significantly improved age estimation accuracy, and the LLM adapted response tone based on age, and the TTS system produced high-quality age-appropriate voices. Our results suggest that personalization by user attributes like age can greatly enhance human-AI interaction. So thank you very much for listening. I'll be happy to answer any questions.
So let's thank the author with a warm round of applause. Just to confirm, you're a high school student.
Yes.
Kokoseka.
Hi.
Okay. First, I would like to commend NICE. I think it's very important that we should empower the next generation of students, especially high school. So hopefully, next year, we should see more high school students in Oriental COCOSDA. And I would like also to challenge other institutions to do the same. Okay, do we have questions from the audience? Oh, I think we have a question there.
Okay, hi. So yeah, one quick question. I wonder why you decide to use 95 layers covering all possible ages rather than maybe using like a bin of like adult, young adult, kids, and baby, something like that.
So you mean why I estimate 5 to 95?
So you're using 95 layers covering all possible ages between 1 and 95, right? My understanding about the final layer in the SSL.
So I may so it is so you mean why I estimated one 5, 6, 7, 8, 1 year grid.
You have like, my understanding you're using like estimate the age, right? So you have an input and then it says what is the age of the audio, right? Is that is my understanding correct about your SSL model?
So sorry, please speak in more slowly.
Oh, okay. Sorry. Okay. So I wonder why did you decide to use kind of a regression where you predict the age of the user? I think there's another possible solution where you can actually predict the age group. For example, you predict whether the voice comes from a teenager or from a child or from a young adult or elder.
Yes.
Yeah, so that's my question. Thank you.
So I see. So so in the graph, I made the each scores, so 10s and 20s and 30s. So I think I don't have to estimate by one grid.
Okay, I think we'll accommodate the last question over there.
No, actually, I just ask the co-author answer your question. So your question is about why we under 30 and about 30 for the result evaluation, right? It's because actually the you can see for MAE result the age is the result is not unstable, but in the so we separated 30 this age is because make it more stable. So basically for the people before 30 years old, it's more it's basically you can say they are still teenager, right? But after 30 years old, basically you can say it's more you need more respect. So that's why we separate it is 30 years old. Is that can answer your question? Yeah, thank you.
So thank you for that. This is an interesting topic, and I would like to also encourage discussion after the session. So again, let's thank the author with a warm round of applause. Again, I'd like to commend NICE, especially Sakyani Sakti, for encouraging the youth to participate in Oriental COCOSDA. Hopefully, more to come in the years to follow. So let's move on to our next paper, Enhancing Indonesian Deepfake Speech Localization with Pathological Features. The authors are Edia Zaki, Naufal Ilman, Desi Puji Lestari, and Kandi Olivia Mawalim. So the floor is now yours.
Okay, good afternoon, everyone. My name is Edia Zaki Naufal Ilman. I'm from Institute Technology of Bandung, and I'm here to present my work, which is a joint research with my supervisors, Dr. Desi Puji Lestari, also from Institute Technology of Bandung, and Kandi Olivia Mawalim from Japan Advanced Institute of Science and Technology. This work, the work I'm presenting is about enhancing Indonesian deepfake speech localization with pathological features. So let's get started. Let's get into the background or introduction. So with the rapid development of AI, deepfake voices, deepfake audio has been increasingly realistic. While this technology has many positive uses, it also possesses serious risks, voice impersonation, misinformation, or fraud. And detecting a fully deepfake audio is challenging enough, but partially spoofed audio is a bit more challenging as it's only a small part of the audio is manipulated. Maybe just a few seconds from a very long sentence and so on. And so simply detecting whether the whole file is, or the whole audio is real or fake is not enough. We also need to localize or find which part of the audio that has been manipulated. And so we get into the speech pathological features. And so speech pathological features refers to features that is widely used for typically medical cases, such as Parkinson's or any other voice disorders. And so recent studies have found that both disordered voices and deepfake voices tend to share some similarities, specifically in unnatural acoustic traits like irregularities in pitch, loudness, and even voice quality. And so the idea is, if pathological features can describe how a person's voice deviates from natural speech or patterns, maybe they can also help us detect deepfake voices deviate from natural speech. And so we come to the motivation for this study, which some of the motivations comes from the fact that research for localization for partially spoofed speech in Indonesia is still underrepresented. It is also because the lack of available Indonesian datasets that provides this partially spoofed scenario. Mainly available partially spoofed datasets are focused on usually English and Mandarin. And the second motivation is, although speech pathological features may have been used for detection, but their potential for localization where the manipulation occurs has not been explored. And so this is why in this research, we aim to enhance Indonesian deepfake speech localization by combining these newly researched speech pathological features with spectral features such as LFCC. So we get into the related works. Several datasets have been developed for partially spoofed audio, such as half-truth audio detection, or HAD, which is a partial spoof audio dataset focused in Mandarin. For localization system, there also exists CM, which uses LCNN and BiLSTM that has been used for segment-level detection using LFCC. And for the research in speech pathological features, it is used ResNet-based models with score fusion of using pathological features and MEL spectrograms. However, none of these specifically focus on Indonesian speech. And the aim is to combine these two types of features, which is speech pathological features and this localization system, which currently has no research been done. So we get into the methodology. First, we go into the dataset construction, because currently there are no available datasets for the partially spoofed one. And so we created it first for the bona fide or the genuine speech. We compiled it from two Indonesian speech corpora, which is Common Voice, which is a widely used open source dataset that contains diverse speakers, accents, and varying recording qualities, and also Prosa.ai, which is an AI company providing proprietary speech data and language technology resources. And this combination allowed us to include both open source and studio quality recordings, so our dataset could represent a more diverse real world conditions. We get into the fully spoofed part of the dataset, and for the fully spoofed dataset, we use several text-to-speech models, and using the same transcripts of the bona fide audio, we feed it into the text-to-speech, generating synthetic voice, and that synthetic voice is also fed into a voice converter with the original voice used as reference to make a synthetic voice that is more similar to that of the original voice. And something to note is that one of the text-to-speech models was actually reserved during evaluation to test whether the model can generate, to unknown synthesis systems. So one of these text-to-speech models that are used are not used, the data set it produced is not used for training and only used for evaluation. Then we get into the partially spoofed one. So in this subset, we actually created two scenarios, which is bona fide to spoof, or B2S, which is inserting bona fide parts or real parts of an audio to a fake part, and spoof to bona fide, which is embedding a fake segment into real audio. This setup is actually to make the dataset more diverse and balanced, helping the model to learn, recognize synthetic boundaries accurately. So we get into the model and training settings itself. So as I said, we used a combination of LCNN, or Light Convolutional Neural Network, with BILSTM. And this is because this is actually the same architecture used in a previous study that is also research in localization, but with different features. And this LCNN itself is actually one of the best model during the ASV Spoof 2019. And for the training, we used 50 epochs, a batch size of 16, and a learning rate of 3 times 10 to negative 4, which is half also every 10 epochs. This setup was applied equally to all models so that the performance difference comes purely from the features itself. So we get into the feature extraction. So there are actually two features that will be extracted, which is LFCC and the pathological features itself. So for the feature extraction process, we'll be using a 20 millisecond analysis window with a 10 millisecond frame shift. And so this keeps both feature types aligned in time so they can be concatenated for the combination of these two features. This is the visualization. So from the same audio, it will be extracted LFCC and also these pathological features, including their first and second derivative, and then we concatenate them to be one representation. And this is the system overview, as you can see in the slide. So from the input audio with the duration of D, and then it has its feature extracted resulting in a representation X, which has the length of N, which is the division of D, which is the duration of seconds of the audio itself, divided by the frame shift, which in this case is 10 milliseconds. And then those features is also feed into the LCNN and BILSTM, creating a representation of H with the length of M. This M itself is the division of N with L, which is the amount of stride or the convolution factor of the model itself, which in this case is 16. And then we got into the cosine similarity, creating predictions for each segment with the same length, which is M, deciding whether that part of the segment is real or fake. This is an example of the prediction. So if you can see, there's actually a segment where a real part and a fake part is in the same segment, in which case it will also be regarded as fake. So let's get into the results. So we get into the dataset itself. The constructed dataset results in an approximately about 31,421 data. And we get into the first model evaluation using all test data. We can see that pathological features alone cannot beat the baseline, which is LFCC. And meanwhile, the combined features of LFCC and pathological features actually beats both the models only using LFCC and pathological features itself. And so it has an accuracy around 99%, an EER below 1%, and this best metric is across all the other metrics, not just one. So the next, we get into the model evaluation for the unseen test data, which is the synthetic data that which the model didn't use for the training. And as we can see, there is a bit of a reduced value, but not too significant, and the value itself is still quite high, and so it kind of it shows that it is still quite robust. And also the fact that LFCC, the combination of LFCC and pathological still beats the other two models trained using only LFCC or trained using only pathological features. And so this is a bit of a comparison between the unseen test data and all test data. There isn't a bit much of a difference. And so we go into the conclusion that in summary, we successfully built a dedicated Indonesian deepfake speech dataset covering both bona fide, fully spoofed, and partially spoofed scenarios. And we also learned that the model trained solely on pathological features did not achieve better accuracy compared to the baseline using only LFCC features. And the model trained with a combination of both LFCC and pathological features outperformed both LFCC-based and pathologically based models, showing improvements across all evaluation metrics. And for the future works, it's to expand the dataset, as the dataset itself is still relatively small, and the model, TTS model use is also still quite low. And so we want to increase the including more synthesis methods, including more TTS or maybe voice conversion models. And also, we want to explore more feature fusion. We want to explore combining with other features, maybe CQCC and other features. And we also want to experiment the effective size of frame for extraction and segment size of predictions, since we only able to test 20 millisecond and 10 millisecond frame size and hop size, and resolution is same. We didn't experiment, and we want to explore further, and so we want to see which part is most effective and precise. And finally, we want to test this on cross-lingual data to see if these features generalize beyond Indonesian. And that is all for my presentation. Thank you so much.
Thank you very much. Let's thank the author with a warm round of applause. I think we have time for one quick question or comment. Do we have? Yes.
Thank you. From the title, it said that it only applies for in Indonesian language. So I think that deepfake should be applied not only in one language specific, but it also should be applied in other languages. So my question is, can it be generalized for other languages? And my second question is how to combine between the pathological speech feature with LFCC. I mean, what is the exact dimension, the size, and how to combine it for, I think you also derive some derivative from LFCC and the pathological. So that's my question. Thank you.
Okay. For the first question is it applicable to other languages, right? Or, yes, so technically it should be able to, but since we are, for this study, the scope is only for Indonesian speech, so it is our future, it's a future work to test other languages, but in theory it should be possible, since for LFCC and pathological features itself, it shouldn't have any significant difference between other languages, since the pathological features itself is actually focusing on the variation of, say, frequency amplitude, which is unnatural for like disordered voices. So technically it should be applicable to other languages, but we do need to test it on, to implement it to other languages to be able to explore it more further. But for the second question, it's, what was it? Excuse me?
What is the exact dimension for pathological speech and
okay.
LFCC, and how to combine
So for the combination itself is actually just concatenation. Since the LFCC and the speech pathological features itself is using the same extraction parameters, which is a 20 millisecond frame window and a 10 millisecond frame shift, it actually generates the same amount of segments of features. And so what we did is just concatenate them for each segment. So LFCC segment 1 with pathological features segment 1, and then continue LFCC segment 2 with pathological features segment 2. Their amount is the same since the extraction parameters is also the same.
What is the dimension, the factor, 100 or?
Since the audio itself is actually dynamic, it doesn't have any certain dimension that needs to, there's no standard. And so actually the size is actually, depends on the audio itself.
So it's frame based, right? It's based on each frame.
Each frame?
Yeah.
The size of each, the resolution for the, the resolution for the prediction, right? Oh, so it's actually 160 milliseconds, and this is because of the, one of the factors of this 160 milliseconds is because of the convolution factor, which is the stride of the architecture. So that's it.
Thank you.
Thank you. Thank you for your question.
Okay, due to time constraint, we will end here. So let's thank the speaker with a warm round of applause. Discussions, of course, are encouraged even after the session. So we will now go to the last paper for this session. I believe the authors will be connecting online. So a deep learning approach to low-resource Sanskrit speech recognition using CTC laws. And the authors are Suhani, Amita Dev, and Poonam Bansal. Can you hear us?
Yes, sir. Am I audible?
Yes, we can hear you. The floor is now yours. Please begin.
So a very good afternoon to all of you. Let me introduce first myself. My name is Suhani and I am from New Delhi, India. Today I am presenting the paper entitled A Deep Learning Approach to Low Resource Sanskrit Speech Recognition using CTC laws. The content of my presentation would be like introduction, contribution, dataset, methodology, results, and then conclusion. So Sanskrit is a classical language of India which serves as a forum for academic and philosophical conversation. The Hindus' granthas like Mahabharata, Ramayana, all are written in Sanskrit language. There are at least 40,000 native speakers exist in India. Sanskrit is among the 14th original language of the 8th schedule to the Constitution. It stands out for its intricate morphology and great lexical production. Many modern languages like Hindi, Bengali, Gujarati, Punjabi, Assamese evolved from Sanskrit, but an effective and efficient search system is not yet available for recognition of Sanskrit language. So it draws attention of many researchers to build such a system that helps in the revival of Sanskrit language by building an effective ASR. So there are some features of Sanskrit language which is very challenging for us, it includes 13 vowels, 33 consonants, and the numbers are singular, plural, and dual. Genders are male, female, and neutral. And the type of vowels are short, long, and compound. And really, the compound vowel is very challenging task for creating SR system for Sanskrit language. And the order of words in Sanskrit are not significant. Types of tenses would be present, perfect, imperfect, aorist, paraphrastic, future, simple future, and conditional. The contribution of my paper is to contribute to the revitalization and preservation of the Sanskrit language through the development of an efficient and robust ASR system, to develop an end-to-end ASR system for the Sanskrit language using a CNN plus by GRU hybrid architecture optimized with CTC laws, to efficiently handle the complex phonetic structures, sandhi formations, and scarcity of annotated data by leveraging convolutional layers for local feature extraction and bidirectional GRU layers for contextual sequence modeling. And finally, I have evaluated and optimized model performance using key SR metrics such as CER and WER. In this research, I have used the data set that is known as Vakyans. It consists several hours of Sanskrit audio with their corresponding transcripts. It mainly covers text from slokas, Shastra, radio programs, and Sanskrit literature. We have used 6 speakers, and the size of data set sentence is 7,158, which includes 12 hours of total duration, and its sampling rate is 16 kilohertz. So here comes the methodology part that I have integrated into the Vakyans dataset. The proposed methodology for Sanskrit speech recognition follows deep learning pipeline designed to convert raw audio into accurate transcriptions. The process begins with audio preprocessing, where recorded Sanskrit speech samples are cleaned, normalized, and transferred into spectrograms. Corresponding text data is tokenized into subword or character levels units for alignment during training. These spectrograms are then fed into the input layers, followed by a series of feature extraction and sequence modeling layers. Initially, convolutional 2D layers with batch normalization and ReLU activation capture local spatial patterns from spectrograms. The data is received and passed through multi-bidirectional GRU layer with dropout, which effectively model long-term dependencies in both forward and backward directions. A dense layer with ReLU activation refines these learned representations before applying the CTC loss, enables the network to learn without requiring the pre-aligned input-output pairs. During inference, the model applies a softmax layer to generate probability distribution over possible tokens, followed by a decoding to produce the most likely transcription. The architecture efficiently integrates convolutional and recurrent modeling units with CTC loss to achieve accurate end-to-end ASR system. These are the parameters and the values that I have implemented. Like in the decoding part, I have used beam search decoding, and the loss function is CTC loss function. So here come the results. I have achieved a word error rate of 41% and character error rate of 22%, and we have generated predicted test corresponding to target state each epoch wise. Like I have run all the model till 20 epochs, so this is the generated and target predicted test, and here is the curve that shows the training and validation loss over epochs. So here we conclude our presentation that this work presents an end-to-end automatic speech recognition system for the Sanskrit language using the model similar to deep speech 2-bit CTC loss. The corpus of 12 hours for Sanskrit audio has been trained, and despite the challenges of limited resources and the complex linguistic structure and phonological complexities of Sanskrit, the system achieved a WER of 41%, highlighting its variability of transcription tasks in low-resource language, and the model effectively learned audio-text alignment from spectrogram features without requiring explicit phoneme-level segmentation. This contributes to the ongoing efforts of bringing technological accessibility to classical and under-resourced languages. Future developments like we can integrate beam search decoding with an external language model, data augmentation techniques, and larger, more diverse data sets are anticipated to improve recognition accuracy, and we can also implement weighted finite state transducer decoding so that our accuracy can lowest to under 20%. So that's all from my side. Thank you.
Thank you very much. Let's thank the speaker with a warm round of applause. Do we have questions from the chat? Are there questions from the chat? Okay, do we have questions from the audience? So I'll probably start. I have one clarification. In your slide, I think it's slide number 1, you mentioned 40,000 native speakers, but in the paper, it was mentioned that the number of native speakers in Sanskrit is at least 2,400. Could you clarify which one is correct?
Sir, actually in India there exist 40,000 speakers of Sanskrit language. But in my data set, I have used one, actually the data set of Sanskrit language is not exist. We have taken some from radio programs or from Ramayana or Gita to create a simple corpus of Sanskrit. So it has only 6 speakers.
Then the 40,000 native speakers, are these L1 or L2 or L3?
Sir, 40,000 speakers exist in India in a state called UK Uttarakhand state. They are the native citizens. They always speaks in Sanskrit language.
And then finally, you were able to achieve 41% word error rate.
Yes, sir. Without using any language model, we have achieved 41% word error rate.
Comparing to other works in this language domain, is this a high number or a low number?
Sir, this is really a high number. We will definitely try to reduce this number.
Yeah, so I think that's one future step for the study. Do you have other questions from the audience here? Okay, so if there are none, let's thank the speaker with a warm round of applause. Thank you very much.
Thank you very much.
So I now close the session. So this is again session number 6, oral session number 6. So up next we have the gala dinner. So I will turn over the floor to the organizing committee for announcements.
Thank you very much to 4 group speakers on site and Ms. Suhani, who presented online. Thank you very much. And of course, we also thank our chair session, Professor Nathaniel Oko. Please have a seat. Distinguished delegates, ladies and gentlemen, the 6th session were our last session today, but not least. As the professor said, we will continue to gala dinner here in this auditorium Koinonia. But before that, allow me to remind you of the 3rd and last day of the 28th International Conference of Oriental O-COCOSDA tomorrow, Friday, November 14, 2025. Our 3rd day will start at 8 a.m. and with the 7th oral session and closed with city tour to Borobudur Temple. So for you who will check out the hotel in the morning, you can put your luggage in the concierge. Our concierge will be our reception desk. So you can put your luggage upstairs in the desk besides our entrance gate. And also, please don't forget, tomorrow wear this t-shirt. Okay, hopefully for all of you who just joined in here, don't forget tomorrow please wear this t-shirt. You can find it in your goodie bag that committee gave you yesterday. Okay, so we are preparing to have fun. Committee already show you where you will visit tomorrow. So now it's time to relax and enjoying the gala dinner. I will give you 5 minutes if you need to go to the restroom before we start the gala dinner. So please take your time. We will start precisely in the next 5 minutes. Thank you. Ladies and gentlemen, okay, I think all of you already returned from the restroom. We may have our afternoon photo session before the gala dinner, but this time you don't have to go on stage. Just stay in your table, stand up please, and the photographer will take the photo from the stage. So we will have a different background this time. Okay, once again, if you don't mind, please stand up for a while. We will take afternoon photo, last photo of this day, from the stage. The photographer will take it from the stage. Okay. Okay, everybody's ready? Everyone's ready? I will count from 1 to 3, and then you can give us your sweetest smile, please. Yep. Okay. 1, 2, 3. Okay. Change pose. 1, 2, 3. Okay. This will be a perfect photo if you need to upload it in your own social media. Thank you very much. Have a seat, please.